today we'll discuss another very important physical application of the method just discussed. It's so-called Aharonov-Bohm effect. So what's this effect about? Suppose we have an infinitely thin solenoid. In the experiment, it may be just a solenoid of the small radius, and the radius should be much smaller than the length of the solenoid. As you probably remember from the general physics course, the field configuration around the solenoid is as follows. There is a uniform magnetic field inside, and there is no magnetic field outside. However, as you know, the magnetic field itself is given by the corresponding vector potential. And though there is no magnetic field outside the solenoid, still the vector potential is present. Usually its configuration is like a circular lines, are the field lines of the vector potential. The question is, what's going to happen if we send a quantum particle and make it scatter on this solenoid? Let's consider the case of infinitely thin solenoid. Then what we expect is that since there is no magnetic field around the solenoid, and all the magnetic field which is present just at the origin. Suppose here is our coordinate system, and here is the origin. The particle shouldn't be able to feel the presence of magnetic field. So for example, such thing as the scattering cross-section should not depend on the value of this magnetic field or magnetic flux, for example. But the correct quantum computation shows that there is actually a dependence of the scattering cross-section on this, or the strength of the magnetic field. And it's quite amazing because what happens actually is that somehow the quantum particle feels the presence of their vector potential rather than the magnetic field itself. And this effect is called an Aharonov-Bohm effect. So let's jump straight into it and figure out what is actually happening on the level of Schrödinger equation. So far so good. Now let's introduce the actual formula for their vector potential. The vector potential for an infinitely small solenoid is giving, well, it's easy to introduce the polar coordinate. So here r is the radial vector, the radial coordinate, and theta is the polar angle. And the vector potential is given by the following formula. It's F divided by 2 pi r times E theta, where E theta is the unit vector which is directed along this polar rotation direction. One can compute the rotor of the vector potential, which naturally gives us the vector of magnetic field. And if you remember the value, the formula for the rotor in polar or cylindrical coordinates, the only non-zero component of the rotor is actually the vertical, the z component, and it is computed with the help of the following formula. In fact, the very derivation of this formula assumes implicitly that a function should be differentiable function of r and theta. So we see that there is no r component, only a theta component. And once you multiply a theta by r, you see that the product is independent of r variable, it's constant, and hence this rotor gives you identical 0. So no magnetic field everywhere, with the only exception of the origin, because when r equals 0, then this formula can't be applied altogether. However, we can still use, for example, the Stokes theorem. So let's write it down. So the flux of the magnetic field through through some circular region which encompasses the solenoid can be computed using the Stokes formula. If we remember that the H field is given by the rotor of the vector potential. Oh, sorry, there is no closed contour integral, it's just the area integral. And this integral can be reduced to circulation of the vector potential around the edge of this area. And this circulation is very easy to compute, because the only non-zero component is again the polar component, which basically glides along this circular edge. And the area itself, suppose it's a circle of radius r. And then, so dr vector is always collinear with a vector, and the scalar product is given simply by phi over 2 pi r, and dr is simply r d theta, which gives us phi over 2 pi d theta. So when you compute the circulation, you get the flux. So you basically integrate over theta from 0 to 2 pi, and you get the flux is given by this phi letter. Now we understand the physical meaning of this parameter. Great. So so there is no, though there is no magnetic field, still due to the presence of the field at the origin, there is a non-zero flux. So far so good. Now let's write down the corresponding Schrödinger equation. And here it is. Here R psi is the wave function, A is vector potential, and m is the mass of our incident quantum particle. As you probably know, the presence of the magnetic field can always be gauged out in any Schrödinger equation. And here, the corresponding change of the wave function is almost obvious. For example, you may introduce the gauge rotated wave function, which looks as follows. It's e to I e over c h bar times the contour integral of the vector potential times dr. So now times the new wave function, which we'll denote with small psi symbol. So now, if you, there is h bar constant here, of course. So if you now compute the value of the gradient, then what you'll get is as follows. So you differentiate the whole thing as a product of this exponential and this psi small function. So the derivative of the exponential simply gives you a over c times e. And the derivative of psi gives us minus ih gradient of psi. Multiplied by psi by the same exponential. And once you plug in this gradient into the original Schrödinger equation, you see that this term proportional to vector potential disappears completely. The only remnant of the presence of the magnetic field is present in the boundary condition, because our wave function, psi capital, should be single-valued in the entire two-dimensional region, I mean x and y region. And that means that psi capital of 0, sorry, not like this, psi capital of r and 0 polar angle should coincide with psi capital of the same function taken at the same point but at angle 2 pi. And hence, the boundary condition for this psi small function is slightly different. So let's switch to another palette to see how this new boundary condition looks like.